button. Okay, let's go through this program. Okay, this echo program we tested before, right? It is very simple program, right? So first one is initialization, the same initialization, right? You set up operating condition, right? You go through that, macro if you want this init, then the next, the main function is very simple. This only few lines of the code, right? So this one, TX54, the location, right? RX54, TX54 location, same location, right? Same location. And this one is a status register, right? During normal operation, I told you there are three kinds of registers. IO device should provide. The first one is configuration register, right? Before normal operation, you have to set up operating condition, right? So the names are different, but essentially that is setting up operating condition. And second category, data register. So in UART case, TX54, RX54, there is data register. To send message to your PC, you are writing some characters to this TX54, hello, for example, right? And through this RX connection, you can receive message from PC to this RX54, right? Data register. And the last one is status register. That is recording. That is recording the status of the UART. It is running okay, or some abnormal event happens. That register is recording that information. Okay, so status register, and this one is the information. This one is the information about status register. Okay, so RX54, then channel status register. So what it says, look at this. 32-bit register, right? 32-bit register, and the first bit, second bit. Second bit is important. This one is indicating 54 RX54. RX54. RX54 is empty or not. Okay, this RX54. This RX54 is empty or not, meaning that UART has received any message from PC or not. Right? That is indicating. Empty means what? 54 is empty, right? This 54 is empty. That means it has not received anything, right? So look at this. So it is reading. Okay, R1. So the CPU is reading from this location, meaning the status register, right? You are reading status register into R2. So then you are doing AND operation, R2, and second operand. What is this? 1, constant. Shift left by 1 bit. Shift left by, so that means you are creating 1, 0 in binary. Right? So you want to do this operation. You want to do AND operation, right? R2 AND everything is 0 and 0, 1, 0. Last 2 is 0. So you want to do AND operation. So why do you want to do this AND operation? To take out second bit. Second bit from status register. So this register, this bit, to take out, this bit, right? So next line, compare. R2 is equal to 1, essentially this number, 1, 0. That means RX54 is empty. Empty means it has not received anything. UART has not received anything from your PC. So you keep, look at this, BQ. Keep checking status register. Keep checking. Right? And if you have received, meaning that if you have received a message, meaning RX54 is not empty. If it is not empty, then you go through. You go through. Right? So then LDR read from R0. R0 is what? R0. TX RX54 data register from RX54. So read from RX54 and read from RX54. Okay, then write the same data to TX54. So you are doing this operation, right? So read from here, then write to TX54. Echoing, right? You are echoing. You are doing, you read from RX54 and write to TX54 and send it to the PC. So you're essentially, you are echoing that message to the PC to display the character you typed from your PC, right? Then what is the next line? This one, compare R3 is equal to 13. If the received message, received character is equal to 13, what is 13? 13 is carriage return. So if you type enter, right? Enter in your keyboard, then PC is sending. You type this enter. Then PC is sending 13. So that means carriage return. Next line. And then what do you want to do? Then you are sending what? What does that mean? You are sending what? You are sending. So here, you received R3 13. Okay, 13. Then you are echoing 13, right? So next one is checking. Okay, the character is 13. Then I want to send one more character, which is 10. 10 is line feed. Enter means next line and line feed. Go to the first column. Right? Enter means hello, right? Hello. Next line, that is line feed. And carriage return. You go to the first column. So this character, this one is 1 3, and this one is 10 in ASCII. So you want to go to the next line. So I'm sending one more data. Look at this. Compare the data you received. Okay, the data you received is 13. Then that means you typed enter. Then I want to send one more ASCII code. Okay, move equal. Okay, R4 is 10. Then you are storing 10 to TX54. Okay, 13 and 10. 13 and 10. So 13 and 10 will be sent to the PC. Okay. Then keep receiving. Look at this. Look. Keep doing this. Any question about this? Echo? Empty FIFO, so what do you think, Hechang? What would happen if you read from empty? Okay, RX54 is empty. That means there could be some junk information. It is not valid information, some junk information, right? So you are still able to read, but the data is junk, right? So why do you want to read from empty FIFO? Probably Hechang. That is the question, right? The answer is you're still allowed to read from RX54, but junk information, right? Does it make sense? Any other questions? Okay, any other questions about UART? Nothing. Everything is clear, or don't know anything. Either of these two, right? You understand or don't know anything. You don't have any clue, right? Okay. So if I add some more explanation to probably Haechang asked that question and Juhan asked that question, right? So we are using same location to read from to point RX54 or TX54, right? And these two and so one location, right? Just one location. And the question is, it has 64 byte buffer. Then how would you implement that FIFO in hardware? So if you have some clue how to implement this TX54 RX54 in hardware, then probably this addressing the one location to write to TX54 RX54 would be more understandable and clear to you. So I would implement the TX54 like this. So I'm talking about hardware implementation, RX54, TX54, TX54. So what if I have to implement TX54, I would do this. So I'm going to have pointer, some head pointer. I'm talking about hardware implementation. So 64 byte. So head pointer should be 6 bit head pointer to point each location, right? Each location. And tail pointer also here. Tail pointer also 6 bit, because you have to point each of 64 byte. Okay, 2 to the power of 6, 64. Then as you execute store byte instruction R2, for example R3, so that is R3, the location. R3 contains that location. Then you are writing 1 byte to that location, right? Then let's say it has H, the first character, right? Then H is 48 in hex, right? That information will be written to I think tail pointer, the location where tail pointer is pointing. And tail pointer will be incremented by 1 by hardware, like this. And you write next instruction store byte, same R2, same instruction, but R2 contains R4, okay, R4 and R3. So let's say R4 contains L, okay, then L, whatever it is, L will be written to the location where tail pointer is pointing. Then hardware will increment tail pointer by 1 to point next location. So I would implement this FIFO like this. I would design hardware like this. So one location for this 64 byte buffer. Okay. Then by using head pointer, tail pointer, the data will be added the FIFO. Then the first data will be coming out, right, by hardware. Okay. 11, 50 to 100 hertz BPS. Okay. The first character will be sent out bit by bit. Then head pointer will be incremented to point next character. That's what I would do if I have to implement. I have to design UART FIFO. Okay. Okay, anything you want to say? TX5 is empty in this program. What do you think? TX5, why would you check TX5 is empty? Okay, so, okay, good question. So I think I told you about that, right? First, this program, right? So hello world, right here. So here I'm checking what? Still status register. Then you are doing, so read from R0, right? So R0, reading from status register, stored into R2. So essentially that information will be stored in R2. Then we are doing AND operation with 8, meaning that 8 is what in binary? 130s. 130s, meaning you want to check TX5 for empty. Okay, TX5 for empty or not. Okay, so empty, not equal. Okay, not equal. TX5 is not empty. Then what does that mean? This TX5 is not empty, meaning that it has some information to send out. Right? To send out. So this program is waiting until TX54 is empty, meaning we want to send out, this byte. Until this byte is completely sent out, I'm not going to do anything. I'm going to wait. So this implementation is not, again, this program. This program is not fully utilizing this 64-byte FIFO. Okay, it is just using this 1 byte. So Jiun, very good question, but this one is this program as an example. Okay, I want to send byte. Then until this byte is completely sent out, I'm not going to do anything. I'm going to wait until this byte is sent out. That is the one. But you don't have to. In this case, you don't have to check out. TX5 for empty bit. You can fully utilize the 64 bytes if you want. Keep writing value. Keep writing value, right? So you can keep writing H E L L O. You have enough buffer to store hello world message. Right? So in this case, right? But again, as an example, this is an example, right? You don't have to check, right? But I want to send out byte by byte. Okay, any other questions? Okay, that is about UART. Okay, now we can switch to next IO device called timer. Right? Next one is timer. This one is also super simple IO device. So timer, okay. What is this? This is alarm clock, right? So you set this alarm clock. These days you don't use alarm clock, you use smartphone, right? But anyway, you set this alarm clock before you go to bed, right? You set time 6, not 6, right? 9 a.m. right? 9 a.m. right? 9 a.m. for too early, 10 a.m. right? You set up the time, then in the morning the bell will ring, right? So you manually set up the time, right? In alarm clock case, but timer IO device, you set time using software. That is the only difference. Same function, Okay, you set up some time. Okay, every sometime, please let me know. That is the function of the timer. Very simple function, right? For example, every 1 millisecond, please let me know. Okay, time is elapsed. Okay, that is the main function. Okay, and inside the CPU, right? So there's Zynq device. Zynq device, we have two CPUs, right? Two ARM CPUs. Inside each CPU, you have two timers. One is called private timer. The other is called watchdog timer. Okay, and you know, three more. Global timer, triple timer counter, and watchdog timer. Okay? So the function, the main function is the same, right? You set up the time, and time is elapsed, then timer will let you know. Okay. So let's talk about this private timer. Okay, inside the CPU. Very simple function. This one, Chaeyeon, can you please?
Private timer, 32-bit decrementing counter, generates an interrupt when the counter reaches 0. Single shot or auto reload configurable. The configurable initial value use peripheral clock.
Okay, done. Okay, it's so fast. No time to break. Okay, 32-bit things. 32-bit decrementing counter. You have 32-bit counter inside this timer. Okay. So inside this timer, the register is called the counter register. Second one. This one, counter register. The size 32-bit. 32-bit register. Okay. So so there is counter register. So counter register can start probably with 1000, depending on the value you set. Depending on the value you set in load register, first one. Using a store instruction, for example, R2, R3, that location. Probably you can write 1000. It has 1000, for example. So you write 1000, that information will be copied into counter register. Okay, then this counter value will be decremented every. So from 1000, 999, 998, and so on. So every rising edge of the clock, this clock. So some internal clock, okay? Some clock, using some internal clock. It is cooking up some clock. Using this clock out, okay? This value will be decremented at every rising edge of the clock. So the value becomes 0, then something happens. So it is counting down from 1000 to 0, counting down. Okay? So it becomes 0, then something happens. But what happens? Depending on the setting, configuration register setting, interrupt can be generated. We will talk about that interrupt later on. Okay, not today. Probably after midterm exam. Okay. So you can set single shot mode or auto reload mode, meaning that single shot. Okay, count down this value. Count down only one time, 1000 to 0. That's it. No more counting. But auto reload mode means 1000 to 0 and start again from 1000 to 0. Start again to 1000 to 0. You keep counting. Keep counting by loading this value to here. Keep counting, counting, auto reload. That value will be automatically reloaded to counter register after this value became 0. Periodic counting, in other words, periodically. Okay? Single shot, only one counting down, and periodic counting down with the value you set in load register. Okay? So that is a function, super simple. Right? So you have only 4 registers. Okay, load register, the thing you program, okay, and counter register. Okay? So those are called data register probably, and control register. Control register is configuration register. Before you use counter, you have to set operating condition. Okay? Configuration first, then normal operation. Okay, using data register, then some status information, status register. So control register. Okay. So clock. What clock? What clock is the timer is using according to the documentation? Hojun, can you please read this one?
Private timers and watchdog timers are always clocked at half of the CPU frequency.
Okay, thanks. Private timer, watchdog timers are working at half of the CPU frequency. Then the question is, what is CPU frequency? Take a look at this hardware design we are using. Okay, this is the one. Open block diagram. Okay, then click on PS and processing system. Inside the PS, you have 2 ARM CPUs. Click on this to check out some detail about the processing system. Okay, you have two ARM CPUs. Okay, and we have used this UART1, right? So echo program, hello world program used this UART. Okay, and then private timer is located somewhere inside the CPU, inside the CPU. So to check out CPU clock frequency, look at this clock configuration. Look at this. So according to this, the PS information, CPU is running at CPU is running at 666 megahertz. Okay, our CPU is running at 666 megahertz, and timer is using half of this clock frequency. So divided this number by 2, so 333 megahertz. Taking this one as a clock, a timer clock. So let's go back to this PowerPoint. So our private timer is running based on that clock, taking this one as an input and doing some counting operation. So let's talk some more about load register, counter register, and so on. I already explained to you, but let's read. Camden, can you read this one? Can you see?
Hello, can you hear me?
Yeah, can you see?
Yeah. Private timer load register. The timer load register contains the value copied to the timer counter register when it decrements down to 0 with auto reload mode enabled. Writing to the timer load register means that you also write to the timer counter register.
Okay, thanks.
Private
yes, can you please? Yes.
Keep going. Private timer counter register. The timer counter register is a decrementing counter. The timer counter register decrements if the timer is enabled using the timer enable bit in the timer control register. If a Cortex A9 processor timer is in debug state, the counter only decrements when the Cortex A9 processor returns to non-debug state. When the timer counter register reaches 0 and auto reload mode is enabled, it reloads the value in the timer load register and then decrements from that value. If auto reload mode is not enabled, the timer counter register decrements down to 0 and stops.
Okay, thanks. The first one, timer load register contains the value. Timer load register contains the value. Copy to timer counter register. Copy to that counter register. Okay. When it decrements down to 0, when counter value, this value became 0. So counter value became 0. Then this load, the data in load register, will be copied to counter register by hardware. So writing to load register, writing to here using store instruction, meaning you are writing counter register as well, right? Because that value will be copied to this counter register by hardware. Okay. Then counter register is decrementing counter. This one is decrementing counter, starting from the value, decrementing, right, by 1 at every rising edge of the clock. How that is implemented in hardware? Very simple, right? So you have flip-flop, right? Clock, that clock, right? This clock, and that is counter value. This counter value. Okay, and that is fed back, and you are doing -1 operation. Minus one is what you are doing. You are doing addition operation, right? That is -1 in 2's complement notation, right? So you have simple adder, right? Adder, then that goes to here, D and Q. That is counter, right? Very simple. So the value, starting from 1000, you are doing +1 plus this value plus this value, right? That is -1, right? So effectively you are doing -1 operation. Then rising edge of the clock, it is taking picture, right? The flip-flop, right, is like a camera. So it's very simple hardware. Right? So counter value reaches 0 and auto reload mode is enabled. Then it is doing that counting operation again, starting from the value you wrote here. Okay, that is copied to here and keep counting down, starting from the location. Okay? If auto reload mode is enabled. If auto reload mode is not enabled, meaning a single shot mode, okay? Then one counting only, right? 1020. That's it. No more counting, right? It stops. So then let's take a look at configuration register, control register, right? So using a prescaler, you can change the operating clock frequency of this timer. So you are taking this clock as an input, then you can hook up. You can create internal clock. So taking this one as an input, then some module. So module is creating the internal clock. Say timer clock, TCLK, timer clock, right? So using this timer clock, using this TCLK, you are doing decrementing operation. Okay? So using prescaler. So it is essentially divider. So what you want to do is, there is input clock. Okay, input clock, ICLK, input clock, ICLK. Then from this input clock, you want to create the internal clock you want to use for counting operation, right? So for example, like this. So I want to divide that clock by 2, something like this. Make it run 2 times slower. Okay? Like this. So divide that clock by 2. TICLK divided by 2. Then you are creating this TCLK. For example, let's say for simplicity, let's say it is 100 megahertz. Input clock, then T clock is 50 megahertz. So using prescaler, you are doing that division operation, clock divider. The clock divider, this is called clock divider. Clock divider. So hardware is doing that operation, that prescaler. So prescaler modifies clock period for decrementing event of timer register. So example is this. So this is one. So example. So you are taking this one as an input clock. Then there is a goal. What would be clock out? Okay. Assume that clock is running at 100 megahertz. Then you set prescaler to 3. Then this hardware will do that operation. Clock dividing operation. Okay. 3 means you have to add 1. So 4. You want to divide input clock by 4. Then goal is to create this 25 megahertz. So using this 25 megahertz clock, timer is doing counting down operation. Okay. So essentially you want to create a slower clock. This one is too fast. Input clock is too fast. Okay. 33 megahertz too fast. I want to create some slower clock. Okay. It's some slower clock, right? So using prescaler, you can do that operation. Okay, very simple. Right? And then this bit, second bit is IRQ enable, interrupt enable. Meaning if the value, count down the value became 0, then I want to generate interrupt. Okay? So timer will generate interrupt, then notify that event to CPU. And we will talk about that, after intermission. And this bit is auto reload mode. This one is 0, then single shot mode, 1, auto reload mode, periodic mode. Okay, and the first bit, timer enable, 0th bit, timer enable. Okay, enable or disable. Enable or disable. Okay, so Camden, it is based on CPU speed? Yes, so we start from CPU clock, right? CPU clock, which is that number. Then timer is using half of this CPU clock. So divided by 2. Okay, that is clock input. Timer clock input. Then you can further slow down this input clock, okay, to create this slower clock, timer clock. So using this timer clock, using this output, there is timer clock, then hardware will do counting down operation. Okay. I do divide the frequency. But if you want to increase, you cannot, Q1, you cannot increase clock frequency. You cannot. So to increasing clock frequency is very tricky operation. So how to increase? Divide operation is very simple, right? Input clock, output clock. So every rising edge, you are doing inverting operation, right? Every rising edge. So think about digital logic design. Okay, you invert. from 1 you invert target output, right? And now it is 1. This rising edge you invert 1 to 0. So this rising edge 0 to 1 you invert. You are doing invert operation. Then you can create a slower clock. Can you create a faster clock from this input like this? 2 times faster or 3 times faster? Can you do that? Two times faster. How to create that 2 times faster clock? 200 megahertz clock. Can you do that? No, you cannot, right? You have to use very special hardware component called, if you want to do that, you have to use called phase locked loop, PLL. So that is doing that doubling or tripling that operation. You can increase clock frequency if you use PLL, but timer does not support that PLL. 100 megahertz. Using this, that guy can do multiplication or division operation of that clock. So multiply by 2, then you can create 200 megahertz, for example. But timer does not support, that PLL. If we support PLL, then you can increase clock frequency. But normally timer does not provide PLL. Yeah, think about why. Why do you want to use, timer? Think about that. What is the purpose of using timer? Gyun. What do you think? Why do you want to use timer? One good application is, think about operating system. Time multiplexed scheduling. I explained to you, right? When you talk about swap operation, swap instruction, right? Every 1 millisecond time. Every 1 millisecond, you want to switch task. Now, this first 1 millisecond, CPU want to execute. We are talking about operating system, right? Windows or Linux. Okay, so operating system decided to run hello world program during this 1 millisecond, and next 1 millisecond, OS decided to kick out. Okay, you are done. Okay, you go out. I need to run a music player MP3. Okay, next 1 millisecond. Okay, I want to run Chrome, and so on, right? So every 1 millisecond, you are doing context switch, task switching. That is what operating system is doing. Okay, so the question is, how do you measure this 1 millisecond? You have to let CPU, or you have to let operating system know, okay, this is the time to schedule. This is the time to schedule a new task. Schedule out hello world and schedule in that MP3 player. Okay, I want to run MP3, right? Task switching. Okay, so that event, that time indication is coming from timer. Timer is measuring this 1 millisecond, then notify that event to CPU. So 1 millisecond, the time is coarse, very coarse grain, right? So you don't want to use very fast clock, right? The 333 megahertz. The goal is to measure 1 millisecond. Right? So you don't need that fast clock frequency. And then does that mean code would need to change for every different? So Camden, the timer clock frequency is different depending on computer system. Okay, so this one is specific example of Cortex A9. Cortex A9 based system. Okay, so that CPU clock. CPU clock and that clock is divided by 2. This is not the rule, right? This is not the rule. Cortex A9, ARM decided to use timer clock, right? Half of CPU clock frequency. This is not the rule, right? So it depends on the hardware system design. Okay, actually timer clock has nothing to do with CPU clock in most of the cases. CPU clock probably it is running at 3 gigahertz. Okay, timer. Okay, I want to run timer at, for example, 100 kilohertz. Many times CPU clock, timer clock, there's no relationship. It has nothing to do with, right? CPU clock. But in ARM case, ARM decided to use timer clock. Okay, timer clock with this half of the clock, CPU clock. Okay? This is only specific, the example or case. Okay. Any other questions? Okay, let's move on. And there is the one. Then no operation. How do you operate? If you set load register with 100, then hardware will copy. The hardware will copy that into count register, and timer will start counting down that value at every rising edge of the clock. So rising edge of the clock, right? Rising edge. I removed it, right? Rising edge, then flip-flop. Flip-flop is taking picture or input, 99, 98, and so on. Became 0. Then depending on your setting, control register setting, interrupt may be generated. Interrupt. Okay, that event will be notified to CPU. Okay, CPU then stops what it is doing, whatever it's doing, then jump to some code, jump to somewhere to execute interrupt service routine. Next we'll talk about that. Then if you set auto reload mode, then this value will be loaded again and counting down, okay, periodically. Okay, so let's skip this. Then the last slide before showing you a demo. Hojun, can you please? Only the green, this part. This part.
The event flag is a sticky bit that is automatically set when the counter register reaches 0. If the timer interrupt is enabled, interrupt ID 29 is set as pending in the interrupt descriptor after the event flag is set. The event flag is cleared when written to 1. Okay,
thanks. There is a status register. Just one status register. Okay, and 1 bit. 1 bit has meaning. Event flag is sticky bit, meaning it is automatically set. This bit is automatically set by hardware, right? When this counter reaches 0, it became 0, then flag will set to 1. Okay, counter reaches 0, then flag will be set. Okay, then to clear that bit, to 0, you have to write 1. Okay. Status register. So that became 0, 1000, then 0, then this sticky bit will be 1. Okay, it's event bit. And to clear that bit to 0, you have to write, okay, let's say R1 and R2. R2 is the location, okay, and 1. So you have to 1 to the location to clear that bit to 0. it is sometimes confusing. You are writing one to this register, then what? You are not writing one, you are clearing this bit to 0. Okay. So that is what spec says. But if you think about hardware implementation, it is not that hard. Think about hardware. What would happen in hardware? What would happen? You are writing one. You are writing, right? CPU is writing. CPU is providing address and data, right? And some control signal to timer, right? Some control signal. So control means read operation, write operation, and so on, right? And you are writing to that register address, right? To that register with the value 1. Okay, 1. Then that is write operation, right? You are writing store operation. Think about hardware design. I would write this code, hardware Verilog code. If address. So I'm talking about hardware, not software. This is hardware Verilog HDL. Hardware description. This hardware description. Address is equal to status register. Status and write operation and data is 1. Data is equal to 1. Okay, and status register will be 0. Simple. Then taking that Verilog description, that will be translated into actual this AND gate, OR gate, AND gate, OR gate, flip flop, and so on. That will be translated. Okay. So it sounds very strange if you don't have any clue about hardware, but not that that difficult. If you know some about hardware, event flag will be clear to 0. This will be 0 if you write 1 to that status register. But there is a rule. Okay? The private timer designer, hardware designer, implemented this register this way. There is no way. You have to follow that rule. Right? Follow that rule. Okay. Okay, now let me show you a demo. This one, private timer. Okay, private timer. Created project for you. So this project. Private timer, this one. Okay. Private. Oops. Okay, very simple program. First, don't worry too much about this mode change. Okay, mode change. ARM is providing 9 different operating modes, right? So this code, as an example, using reading from CPSR, then writing to CPSR, change operating mode to system mode. But don't worry too much about this. Okay, don't worry too much about this. I want to give you some examples, okay, of using MRS, MSR instruction. Okay, we'll talk about that. Here, private road register. Where's that? Private road. Where's that? Private road register. Type F3. Okay, here. Road register. Where is that defined? CSD zinc peripherals. That header file. Okay. So timer base location. So timer base location is this number, F8, F0 something, F8, F0 something, then offset, right? Load register offset 0, counter 4, and so on. Right? So load register, right? 0 offset, right? Counter 4, control 8, status C. Okay, so we defined all 4 register location. Okay, there is a location of load register, counter register location is this, and so on. Here, loading load register, right? Meaning that this one, F8, F0, 06, 00. Then timer initial. Okay, what is timer initial? I want to program load register. I want to set this load register with that number, 400,000 in hex. Okay, 400,000 in hex and store operation. Writing the number. Okay. And control register. Right? Before you use timer, you have to set configuration, operating condition. Look how this control register information. Okay. So control register information, prescaler. Prescaler occupies from bit 15 to 8. Okay, this 8-bit. So I want to put 10 to prescaler. So I did this. Okay, shift left 10 by 8-bit. Okay, to position the 10 into that location. 10-bit shift. Okay, then R1. I'm doing all operation with R1. That means I want to set bit 210. IRQ enable, interrupt enable, auto reload mode 1. Okay, 7 is 111, right? And timer is enabled. Okay, very simple, right? So what I want to do is here, I want to set prescaler to 10. This prescaler to 10, and 7 means this 3 bits. Least significant 3 bits, 111. Interrupt enable, auto reload mode is 1. Timer is enabled, right? And this code is reading. This code is reading from counter register. This counter register. Let me show you. Counter register. Okay? It is counting down, right? Counting down operation, right? So read from the register. So you would see some numbers decremented. Right? Same location, R0, 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 same location. So that number loaded here will be smaller. Okay, getting smaller because decrementing. Okay. Then what it is doing? Just for fun, right? I'm turning on LED. Turning on LED. F means 4 zeros, 4 ones, right? Okay, we have 8 LEDs here, right? So we have here we have 8 LEDs. 1, 2, 3, 4, 5, 6, 7, 8. 8 LEDs. So writing F means you want to turn on last 4. Okay, these 4. Lower 4 LEDs. 1, 1, 1, 1. 4 LEDs, right? Store byte. Then what it is doing? So this forever loop. Forever, right? Forever, this loop. Okay. Reading from reading counter value, okay, R0, because we are not using interrupt yet. Interrupt will be discussed after midterm exam. So we are using a polling method. polling. You keep checking. Software is keep checking status register. Okay, keep checking status polling. That is called polling. Right? Polling and interrupt. Polling and two different methods. Polling and interrupt. Polling, you keep checking status register or data register and whatever register, right? You keep checking register to see to check out the status of timer. But interrupt is not doing the checking operation. When event happens, it is going to actively notify that event to CPU. Okay, this one is not that efficient method, but for now, let's use that polling method. Okay, because we haven't studied interrupt yet. Okay, it is keep checking. Okay, checking counter value just for I want to check out the counter. Okay, and read the counter and read the status register. R1 status register. Again, status register is this. Essentially, you want to check out if that event flag is set to 1. Event flag is set to 1 here, R6. Then compare. If flag is set to 1, equal, this event flag is 1, then you are doing that operation. EQ, right? EQ, 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 EQ. Okay. Event flag is 1, then you want to execute these 4 instructions. Otherwise, no operation, right? Condition is not met, no operation. So XOR operation, exclusive OR operation. What is R11? R11 is this, FF. Right? 0F. Then you do XOR operation with this. That means what? XOR operation, right? XOR operation is doing inverting operation, right? So you want to do this, right? 0F, then XOR operation with FF. Then what do you get? XOR operation, right? Exclusive OR operation. You are inverting, right? Things. Right? If you do XOR with 1, XOR A, B, Y. Truth table, right? A, B, Y. 0, 0, 1, 1, 0, 1, 0, 1. Y is what? 0, 1, 1, 0. So you are doing XOR operation with 1. 1 or 8 ones, right? And then look at this 1, okay, this one. Then you are doing inverting, right? 0 to 1, 1 to 0. So then you get what? You are inverting that guy. F0. So here you want to invert. Okay, R1 will be R11 will be F0. Then you do store operation. Okay, F0 to R10. R10 is what? LED location. What you want to do is what? You are turning on, this last 4, lower 4. Then counter became 0. Then you turn on upper, 4 LEDs. Okay. Then what you have to do? You have to clear the sticky bit. But according to this status register, to clear that bit, you have to write 1. So I'm doing this 1, 2, R12. Okay, 1, 2, right. Yeah. Status register. Then go back. Okay, go back. Okay, keep checking status register. Okay. So what would you expect from the board? This LED. So every that time interval, lower 4 LEDs will turn on. Next, upper 4 LEDs will turn on. Then this one keep toggling between these two. So that number would be what? If you translate that into actual time, roughly, what would be the time? You have to do this math, right? So here, we start from timer, right? Timer. You are taking that clock as an input. Then prescaler doing division operation. In our example, we set prescaler to 10. We set prescaler to 10. That means you are doing, you are dividing the number, dividing this prescaler, right? Prescaler is 10. That means that will be divided by 11, right? 11. What do you get? What do you get? 333, roughly 30 hertz, 30 megahertz, roughly. Okay. Then using that clock, okay, using that clock, you are doing that is 30 megahertz, right? So starting from 400,000, counting down, right? So 3, okay, F, I don't want to, right? Okay, so and so on, right? So what is the number? So compare that against the number. So 30 megahertz means in 1 second you have this one pulse, right? Then you have in 1 second, within 1 second, you have 30 million mega, right? Million pulses in 1 second. That is the meaning of 30 megahertz. 1 second, you have 30 million pulses. That is the meaning of that frequency, 30 megahertz, right? And you want to count 400, you want to count 400,000, right? 400,000, right? 0.4, is it correct? 0.4, 400,000? 4 million, is it? 4 meg, right? 4 meg. A hex number, right? Hex number. So 4 meg, right? 4 meg, right? That is 4 meg. Because 20 zeros, right? 5 zeros means 20 in binary, right? Binary. 20 zeros, right? 20 zeros, right? So 4 million. So roughly, I want to compute. In 1 second, you have 30 million. Then how many? How in 1 second? How many? Counting down can happen. How many counting down? That to 0. Then again, 400,000 to 0. How many counting down can happen? So that number divided by 4 million, 30 million 4 million. So roughly, eight counting down, roughly. So that means, LEDs will be turned on and off, toggling, very fast. It's a rough computation, right? So that LED, right? So every time the counter value became 0, then you are toggling, 4 LEDs. So 8 toggling will happen in 1 second. I think. Let me show you. Okay, registers. Skip the part. Then R0. R0 is that F8, F0. Okay, so register allocation and timer initial 400,000 in hex. Right. Then store instruction. Okay. Then do set up a control register. Then read from counter register. Take a look at R1 to R8. We are counting down from 400,000, right? So F5. Look at this. R1. 3, 5 Fs. Then R2, 3, 4 Fs, E. R3, T, C, P, and counting down, right? Counting down. Right? Sometimes same number because of what? Timer is slower. CPU is very fast, right? So sometimes same number, right? So something like this. Then LED. Okay. Check out LED on board right here. All LEDs will be turned on like this. Right? Then keep checking. No operation, because R6. Look at this. R6 is 0. Okay, keep counting down. So status register will have 0 here because still counting down, right? So then keep doing this. I don't want to type F5 400,000 times. So let me press F8. Then what do you expect? So LEDs will be changed, toggled, right? Like this. So roughly 8 toggling in 1 second. Something like that. Okay, any question about timer? We are done. We are done about timer. Anything? And if you scroll it, just for your information, if you scroll it down, then it is displaying a lot of information, register information. And check out this MP core, right? MP core. Then here, look at this MP core private. Here, look at this control register here. I think that is the one we set, right? Here, we set prescaler to 10 and IRQ enable to 1. Right? Private time control register and load register. Look at this. Displaying load register 400,000. Right? We programmed 400,000 and counter register also So it is counting down, but it's snapshot. So you know this number 29 something, counting down from the number, right? 400,000. So that is the status. Some, you know, not, you know, the current number, but it is keep executing. It's not reflecting current value. Some, you know, if you stop, and that will be, I think, change it. Stop. Look at this. 3E, then let it go. And stop. The number, right? Counter value. Something like this. Okay, then timer status. Okay, probably you can check. It is providing, you know, some information, a lot of information about some I/O, not every I/O, some, you know, important I/Os inside the CPU. Okay, I think that's it for today. If you don't have any question, I'll see you next time. Okay, bye. Right. Thanks.